In this second video, I'm going to show you how to do exactly the same state transition diagram and how to implement it, but now using flip-flops D. And you're going to see the trade-off, okay, on doing this with a flip-flop D. So it's the same state transition diagram. We have exactly the same, this is the same slide that you see before, that you saw before, the A, B, C, and D. And the first step is to take this and generate the state transition table. So this is the same state transition table that you have seen before. Then the next step is to do the code assignment, and nothing changes. Up to this point, everything is the same, okay? You take the codes and you substitute the state transition table, and instead of using the A, B, C, D, you put the codes, okay? So up to this point, you know, everything is exactly the same. Okay, so if we were in an exam and I asked you to implement this first using JK and then using D, basically you use the same steps that you use for JK up to this point. Now, here is when everything is going to change. After you have the state transition table with the codes, then now is when you need to decide what flip-flop are you going to use. So in this case, we're going to do it with flip-flop D. So for flip-flop D, please remember that this is the truth table for the flip-flop D. 0, 0, 1, 1. But the transition table for flip-flop D is from 0 to 0, you need in D a 0. To go from 0 to 1, you need a 1 in D. From 1 to 0, you need a 0 in D. And to go from 1 to 1, you need a 1 in D. This was covered in another video, okay, in a different module. And so we're going to go back to our state transition table with the codes, and we're going to do the same exercise to populate the maps. So this is a flip-flop, this is a K-map for flip-flop Y0, and this is a flip-flop for Y1. So how does this work? Okay, so we have a 0 and we go to 0. So 0 going to 0, we place a D. By the way, let me just correct, okay? When I say flip-flop Y0, what I really mean, let me just erase it so you don't get confused, is really the input to that flip-flop. So let me just call it D0 and D1, because it's really the input, not the output of the flip-flop. So D0 and D1. So going from 0 to 0, we need a 0 there. So I'm going to put a 0 here, okay? And look that in this case it's only 1K map per flip-flop, because the flip-flop D has only one input. Then from 0 to 1, okay, from 0 to 1, we need a 1, so we place a 1. Let's see, what else do we have here? From 1 to 0, from 1 to 0, okay, we need a 0, so we'll place a 0 there. And then to go from 1 to 0, well, this is another 0. Then to go from 0 to 0, well, we need a 0, but it goes here. Remember, this is a tricky one, because this combination goes here. And then to go from 0 to 1, we need a 1, and the 1 goes here. Now to go from 1 to 0, okay, we need a 0. And to go from 1 to 1, we need a 1. And this is the map. Now let's go and do the blue. So Y1, to go from 0 to 0, we need a 0. To go from 0 to 0, we need another 0. To go from 0 to 0, we need another 0. To go from 0 to 1, we need a 1. To go from 1 to 0, we need a 0. But here, remember, this is again the tricky one. To go from 1 to 1, we need a 1. Okay? and then to go from 1 to 0 we need a 0, and to go from 1 to 1 we need a 1. So these are the maps. How do we group them? Well, we can group them like this, and we can group them like this. So this 0, the equation for this 0 is y1 x plus y naught, or y0 naught x. And then for flip-flop D1, okay, is y1 x plus y0 x. And so these are the equations. Now the question is, what happened with the output? Well, if you think in terms of the output, let's go back to the diagram. The diagram here, the state transition table, is showing us the output, okay? The output does not change, okay? So the transitions here, okay, the transitions here, they are gonna imply different flip-flops and different combinations, but the output does not, okay? So the output remains exactly the same. And in the previous example, the output was this. So in this case, we just keep the same output, okay? There is nothing that we need to do. So the output is not changed by any means, okay? The output remains whatever we have before, and before we have y0 naught, y1, and x naught. Okay, this is the same output that we have for the JK implementation. So if we want to build this, I'm gonna show you how does it look like. Okay, so these are the three equations, okay, and these are the three equations. And so for this 0, look, this 0 we need an OR, and that OR requires an AND of y1 and x, and it requires a y naught and an x, okay, and this y naught is coming from here, okay, and then here we require an AND, an OR, this OR, and then there is an AND for x and y0, and there is an AND for x and y1, and look, y1 is coming from here, okay, and finally the output is y0 naught coming from here, y1 coming from here, and x naught coming from the inversion of this x. Okay, what I want to tell you is, if you see, it was easier to do the maps with a flip-flop D, okay? It was easier to do, because why? There is only one flip-flop, sorry, there is only one input for flip-flop D. In the case of the JK, you need to worry about the map for J and the map for K. That doesn't happen here. So in terms of doing this on paper, it's actually easier to do the implementation on flip-flop D. The problem is, if you see here, this implementation, it looks a little bit more messy than the one of JK. In general, you are gonna need more combinatorial circuits if you use flip-flops D in comparison to flip-flops JK. So the complexity, okay, on paper by doing JK is gonna imply that in general you're gonna have less circuitry in the digital implementation. As I was telling you at the beginning of video 1, this doesn't really matter a lot right now, because in nowadays this is implemented in software many times. This is a computer program, okay, rather than an implementation in hardware. Now, if you're using FPGAs, the FPGA has the macro cell that is inside of FPGA has a flip-flop D, okay? So an implementation in flip-flop D is actually very practical.